Today we start a chapter. It's actually a theory chapter, the chapter of circular motion. Now, in circular motion, say that when the motion of the path is circular, or at least a part of a circle, that is an arc. Now, in circular motion, the various formula, etc., are quite similar to the rectilinear motion formula, but the notations, etc., are different. We shall see what are these. Firstly, let us consider this is a circle and this x-axis, and let us say at any point of time the body is here and it is moving with a velocity v. It is of course obvious that at any point of motion, the direction or the direction of the vector of the velocity is always tangential. If it is here, then also the velocity v is tangential. So first we must remember the linear velocity, normally called v, is always tangential to one point. We must remember. Second point, what is the definition of linear velocity? Linear velocity is the path covered. The path is circular here. So we write circular in the parenthesis. The path on second. Now say at any point of time the body was here, and after 1 second the body is here. So this is the angle which it covers in 1 second. And this is defined as the angular velocity and normally denoted by the term omega. Right? Angular velocity angle time. Now this angle is always in radian. This you must remember. In circular motion, all these angle measurements are in radian. And in radian, and angular velocity omega is in radian per second. There can be an angular acceleration also if there is a linear acceleration. So we write if the body in the circular path acceleration A. If the body moves in a circular path with acceleration A, then obviously there will be there will be an associated angular acceleration there will be always an angular acceleration, and angular acceleration will normally denote by the term alpha. Right? So the radian per second omega is the rate of angle coupling by dt by dt. And so the angular acceleration alpha is like linear motion v equal to ds dt or differential of displacement, and acceleration is differential time velocity. This is for linear motion and this is for angular motion. Further, it is very important to know that in linear motion, we have formulas like number one formula we have. Linear motion we have v is equal to u plus ft. V is the final velocity, u is the initial velocity. In angular motion, at the formula final angular velocity omega is equal to initial angular velocity naught plus angular acceleration alpha. In linear motion, we have S equal to ut plus half ft square. In linear motion, we have total angle covered theta is equal to omega naught t plus half alpha t square. Similarly, there is a third formula in linear motion which says v square is equal to u square plus 2fs, f in acceleration, and there is a similar here is omega square equal to omega 0 square plus 2 alpha theta. So you see the actual equation of motion are very simple. Have another important information. Say an arc of S or in that means if this body covers a distance of say S in time t, then what is the velocity magnitude of the velocity? Magnitude of the velocity is equal to S by t. And what is the theta? Angle theta it has covered. Angle theta is equal to, you know from geometry, angle theta is equal to arc by the radius r. So from here we get that the arc length S is equal to r theta. So from this equation, we get V is equal to R theta divided by time t. Now, theta by t is omega, is R omega. So, V is equal to R omega. This also you need to remember that linear velocity V is equal to radius of the circle multiplied by angular velocity. V is equal to R omega. And similarly, you can find out that linear acceleration A will be equal to R into angular acceleration alpha. These are the information that you need to remember, right? Then we go to the next issue. Next issue is very important. And for that, I create another blackboard here for you. Create another blackboard here for you. And I delete these things. I delete this thing also. And this thing also. Let the circle be here. We anyway need the circle. Now, there is one very important issue. And what is that issue? The issue is if you see the earlier blackboard, you'll find that the velocity was like this here, and it was like this here. Magnitude of this was V, magnitude of this was also V. But you know, velocity is a vector. So its property is defined by the direction and magnitude together. Now, if the direction changes, that means there is some change in the velocity. So we write here, in angular motion, magnitude of the velocity remains same. But the vector velocity changes. Means the direction changes continuously. Direction changes the direction changes continuously. Now, from the basic principle, if velocity vector changes, then there has to be an acceleration. Because you know, acceleration by definition is the rate of change of velocity. So if velocity changes, its vector changes its direction. So obviously there is an acceleration. Now we want to find out what is this amount of acceleration, where it comes from, and all these things. And also, if there is an acceleration, there is a force. So where from this force comes? So let us investigate this a little bit. For that, what I do first, I make this circle a little bigger. Standing a little bigger circle will be helpful. For that, once again, let us take this is the center and this is the x-axis, right? And let us consider that, and this is the time t equal to 0. At some time, before we started the measuring the time, at some angle theta, the body was here. And after a similar angle, travel of angle theta, the body is here. So if these are the two bodies, then what are the velocity vectors? This is the I draw the vectors a little bit large size, otherwise the picture will not be visible to you. This is the velocity vector, say v1. This is the vector v1. And velocity vector here, say velocity vector here is v2. So what is the change of velocity? What is the change of velocity? Want to find out this because average acceleration A is equal to del V by del T. And in limiting condition, this is equal to dV. So we have to find out the change of velocity in the time and the time. So this is a vector. So this is a vector final velocity. This is a vector initial velocity. So change is actually final vector v2 minus initial vector v1. Initial vector v1. So we have to subtract this vector v1 from the vector v2. For subtraction of addition of the vectors, you know that you can always translate and remove the vectors in parallel. So let us move the vector v2 in this here. We put both of them here. Vector v2. For the sake of vector analysis or vector subtraction, we bring v2 here. The result will be all right if this v2, original actual v2 and the translated v2 are parallel. This angle is theta. So this angle is theta. And v1 we take here, we translate it to here. This is v1. This angle is also theta. Now we have to find out v2 minus v1. So we reverse v1. This is minus v1. Vector minus v1. Now a resultant of these two vectors is once again the diagonal of this rhombus. Diagonal of this rhombus. This is the resultant vector, which is v2 minus v1. So it is very important to notice this v2 minus v1 is along the radius. Sorry, v2 minus v1, both vectors, v2 minus v1 is, well, along the radius. Along the radius to complete it, right, towards the center. That means when a body is moving in a circular path, although the magnitude of its velocity, linear velocity, does not change, but its direction changes. And this change of direction produces an acceleration, and that acceleration is always directed towards the center of the circle. This you can find out if you take a small stone and tie it with a thread on your ring with your index finger, and you start revolving the stone, you will find always there is a force on your finger. That means there is always a force and acceleration which is due to the acceleration, which is directed towards the center. Now we have to find out what is the amount of this is we have found out the direction. What is the magnitude of this acceleration? Magnitude of this acceleration. This magnitude we have not yet decided. We have to now find out the magnitude, right? Now here we do one thing. This diagram has become clumsy, so we another circle here, right? And maybe we make this circle a little smaller so that it is visible. We make another circle here, and it is the same. This is the center, and this is the x-axis, and same thing, the two vectors. This is one vector v1. This is another vector v2. Another vector v2. Now let us consider this is the center is O. Let us consider this point is A. Let us consider this point is B. Now, this is a radius. This also is a radius. We join this to make a triangle OBA or OAB, whatever it is. Now, these two vectors, our final velocity v vector was this. This is final velocity v2 and initial velocity v1 vector was this. And if you do v2 minus v1, then actually this is the vector which is del v. Del v, within bracket I write this is v2 minus v1. Minus v1 is this vector. Let us consider this point as P, this point as R, this point as Q. Now from the triangle OAB and PQR, what do you find? This angle is also 2 theta. This angle is also 2 theta. And this is an isosceles triangle. This is also an isosceles triangle. Therefore, this triangle AOB is equivalent to, angularly, this triangle AOB is equivalent to triangle PRB. q. That is so. Therefore, AB, AB is the arm opposite to the angle 2 theta. Here, arm opposite to the angle 2 theta is PQ, and it's the isosceles triangle. Any arm here is the radius of the circle, OA. Here, this any arm, let us say RQ. From here, what we get? AB by OA, OA here, OA or OB, actually radius of the circle, is equal to PQ. PQ is actually del V vector divided by RQ is small v vector. Rather, only the velocity vector. Now, when we measure here, in the diagram, we have shown wide angle of 2 theta. That is for me to draw the diagram. Otherwise, it will become very clumsy, and for you to understand the diagram. But when we actually measure acceleration, or rather velocity, or rather any physical parameter, you know, we have to measure it in a very small time interval. In a very small time interval, right? This is the method of measurement. That means we have to measure it in the limiting condition when theta is almost zero. So, in the limiting condition, theta is almost equal to zero, then AB, this arc AB will actually reduce from here to here, from here to here, and actually it will be the del S, or in the limiting condition, it is the del S. That means the small change in the path, del S by R is equal to, this is del V by V. We do not use the vector sign anymore because we are now trying to find out the magnitude of the vector, magnitude of the acceleration. The direction we have already found, it is towards the center. So from here, what do we get? Del V, which actually magnitude of acceleration, is equal to V by R multiplied by del S. This shows from here, this is, so from here, if we divide both sides by del T, because we have to find out the time differential, del T is equal to V by R del S by del T. And in the limit, this is dV equal to V by R dt. Now, what is dV dt, or time domain differential of velocity? Time domain differential of velocity is acceleration, is angular acceleration A, not angular acceleration, it is acceleration. Angular acceleration is alpha. So, acceleration A is equal to V by R multiplied by ds dt is the velocity. So, this is equal to v square by r. So that means we write here acceleration which is directed towards the center, its magnitude is v square by r. Obviously, if the radius is very small, if the circle is very small, then acceleration has to be high. If the circle is very big, then acceleration is small. And this is one equation that you have to remember. And this also culminates into, since A equal to V square by R, we know, we have seen in earlier code that V is equal to R omega. So V square equal to R square omega square by R. So A is also equal to R omega square. This is one relation of the acceleration. This is another relation. So conclusion is, in an angular motion, there is always an acceleration directed towards the center of the motion. And magnitude of the acceleration is v square by r. Now, whenever there is an acceleration, whenever there is an acceleration, there is a force. Well, you have seen in Newton's second law that force F is equal to mA. So if there is an acceleration, there is a force. Now, think of it. Some body is moving around a circle. Suppose you have a motorbike, you are going in a circle. Or anything moves in a circle. Anything moves in a circle. Then who applies this force? Where from this force comes? In the next episode of this theory, we shall see where from this force comes. But there is a force. So we write, there is a force towards the center. And who applies this force? In case of celestial motions like Earth, Sun, this may be gravitation. In electricity, it may be electric field. In our physical world, like cycling or motorbiking, it may be the friction. And if you tie a stone with your finger, it may be the tension of the thread. These are the various sources of this force. But the force is there. Since there is acceleration. In next chapter, we shall see what is the amount of this force and how this force is actually applied. Okay?